We're going to very quickly look at this free online graphing calculator called Desmos and how functions look. In particular, we're going to look at the graphs of functions, and we're going to use them throughout the semester as visual representations of what the concepts of calculus are doing to the functions. So I'm going to start by defining a function f of x, and we're going to use a straight line at the start. So f of x equals 2x plus 1 is this line right here. You can look at the coefficients of the line and tell exactly what the slope of the line is. That's the number in front of the input. And the y-intercept is given by this number here. So in particular, you'll see it intercepts at the point 0, 1. And the slope of 2 tells us that for every 1 it moves in this direction, it rises 2 in this direction. If I were to change the intercept to negative 1, you can see that it's exactly the same slope, it's just starting at a different point. If I were to change the slope to 3, it's going to increase how much the line rises. It goes up 3 for every 1 I move over. In general, polynomials are combinations of powers of x and coefficients. Something like 3x squared minus 1 gives me a shape that's pretty common and pretty familiar to most of you, I hope, and that's the parabola. When you look at the definition of a function like this, the graph of the function tells you the height based on the input. So the points on here are going to represent two numbers. One of them is the x, which is on the horizontal axis, and the f of x, or the height, is on the vertical axis. So if I want to put a point 1, and then whatever the function value at 1 is, you'll notice that that is the point on the graph. The graph is nothing more than the collection of all of these pairs, these ordered pairs. So in this program, if I want to find the actual value of what f of 1 is, I can just type f of 1 and it tells me what my value is. You can also use this to do composites and to simplify functions, and that's a very useful thing to be able to do. In general, with polynomials, the power, the maximum power here, tells you the number of maximums and minimums that are possible. They're not always going to be as many as there are, but this will tell you the maximum number. And the maximum number is going to be 1 less than this. So this function as a square can only have at most 1 minimum. If I have something that's a cube, then I could have multiples, but in this case it only flattens out and continues rising. I can add another term to this and end up with 1 maximum and 1 minimum. When I say maximum and minimum, we'll talk about more what that means later on in the course. But generally speaking, it's a place where it's larger than everything else nearby. So I have a maximum here and a minimum here. If I were to take a simple function, like the square root of x, we have the graph of the square root of x. Notice that there's no graph over here, and that's because you're not allowed to plug negative numbers into the square root of x and get a real number out. You'll get complex numbers, or imaginary numbers. So if I take a function like this, then the standard graph transformations are going to alter the input or alter the output. So they will look something like this. If I want to take my f of x and add 1 inside the parentheses, I'm changing this into a composite function and using x plus 1 as the input to my function f. In doing so, it takes my original graph and does nothing more than shift it to the left by 1 unit. If I want to shift it to the left by 2, I can do f of x plus 2. And it's still exactly the same shape of the graph. If I do the same thing outside the function, if I do f of x plus 2 outside the function, it doesn't shift to the left anymore, it shifts it up. That's another confirmation that doing something to the inside of the function is not the same as doing it to the outside of the function. The graph looks completely different because it's taking the output of f of x and adding 2 to the height. It's moving it up by 2. If I want to introduce negative numbers into this, negatives do interesting things to my graph. If I take f of x and I put a negative outside the f, it takes my function and it flips it over the x-axis to give me this function out here. So negative f of x is the same function flipped over the x-axis. If I take this negative and move it inside in front of the input, it flips it over the y-axis, and it gives me the exact opposite going in this direction. So You should be somewhat familiar with all the graph transformations, and there will be practice in the problems that'll help you remember them if it's something that you've forgotten. There are 6 basic trig functions. We're not going to use all of them extensively throughout the course, but you should be familiar with the basic properties of most of them. The 2 main ones that everything else is based on is the sine of x and the cosine of x. The sine and the cosine are both periodic functions, which means from where they start, they will eventually get back to that point as you're going from left to right, and what happens after that looks exactly the same. I'm going to change my labels here to label every pi over 2. I think that is not what I want. I want my step to be pi over 2. So when I label it every pi over 2, the maximum value of the sine function, I'm going to turn off cosine for a second. The maximum value of the sine function occurs exactly at pi over 2, and the minimum occurs at 3 pi over 2. This corresponds to the units on a circle. If you remember, the pi's represent radians. So 1 pi is half of a traverse around the outside of the circle. And then it takes 2 pi to get from the start of the circle all the way back to the start again. So the sine function represents the height of the points trapped on the circle. In particular, if you have points on your circle, then the y value of the point on the circle is exactly the sine. So sine of 0 is 0 because this point is my starting point with 0 radians and the y value is 0. Sine of pi over 2 is halfway around the top of the circle, or a quarter of the circle. That gets me to a y value of 1, which is why the sine is up at 1. When we get back to pi, my y value is 0, and then when I get to 3 pi over 2, my y value is at negative 1. The cosine function is defined in a fairly similar way, except instead of taking the y values, we take the x values. So the x value at the start, at 0 radians, is 1. As I go to pi over 2, my x value decreases to 0, then goes to negative 1, and then, decreases 0, goes to negative 1, back up to 0, and then up to positive 1. So cosine from 0 to 2 pi starts at 1, goes to negative 1, and back up to 1. When you apply the graph transformations to the sine and the cosine, you can recover the sine and the cosine again. So in particular, if I look at sine of pi over 2 plus x, I end up with the cosine function. If I look at sine of pi over 2 minus x, I end up with the cosine function. If I were to start changing this, so instead of pi over 2, I can use 2 pi over 2. That gives me back the sine function. If I go to 3 pi over 2, it gives me a transformation of the functions. If I go all the way up to 5 pi over 2, I'm back to the cosine function. These are completely periodic. As you're transforming them, eventually you'll end up back where you started. And the same is true for the cosine. The tangent of x, or we write it in here tan x, is defined as the quotient of the sine to the cosine. It's the sine value over the cosine value. So the tangent of 0 is 0, because sine of 0 is 0 and cosine of 0 is 1. It's 0 over 1. At pi over 2, it's not defined, because sine is 1, but cosine is 0, and you can't divide by 0. When the two cross, the tangent's exactly at 1, because sine and cosine are the same. So what we get is this general shape for our tangent. We have asymptotes at every time the cosine is 0. We get zeros every time the sine is 0, and it follows this general shape. There's three other functions that are fairly typical. The cosecant and the secant are just the inverses of the sine and the cosine. Or by inverse, I mean 1 over the sine or the cosine. So the cosecant of x, for instance, is 1 over the sine. When the sine is 1, the cosine is also 1. When the sine is 1, the cosecant is also 1. It'll have asymptotes every time the sine is 0, and you can see that here and here. And then every other place, it's just 1 over the value. So at pi over 4, for example, the value of the cosine and the sine is both 1 over the square root of 2. At that same value for the cosecant, the value is exactly the square root of 2. So we use the cosecant as a shorthand, but everything can be written in terms of the sine and the cosine. Last step is to look at what compositions do to our functions. So I'm going to change my values back to integer values on the x-axis. I'm going to look at two functions. F of x is 2x plus 3, and g of x as 1 minus x squared. When I compose these two functions together, I'm going to end up with a third function, or a fourth function, depending on the order that I put these two in. When I look at f of g of x, it gives me a new function, which is not any of the two original functions, and it typically won't be, but it's found as a combination of f and g. If you remember, with the composite, we're taking g of x as our input to f. So we're taking this red parabola as an input to this straight line in order to get our composite function. I'm going to very quickly change these so that they're a little bit less prominent. And so the function I'm interested in this blue function, in the composite, if I want to find out what the value at 0 is, I can do f of g of 0, and it tells me the value is 5. And I see that on the function here. But in order to get that value, I needed to take g of 0, which is 1, and you can see that on the graph here. G of 0 is the value 1. We're going to take that 1 now as the input to the other function. So 1 is the input, 1 on my x value, go all the way up to my other function, and that'll be the height of my composite. If you do the same thing for 1, for instance, f of g of 1 is 3. And we can find that by g of 1, which is 0. I take that 0 now as the input to my line, and it gives me a height of 3, which tells me that my function here is going to be at 3. You can view composites this way all the time. It's much easier to actually get a formula for f of g of x, and we can do that by making a new function. I'm going to call it h of x, and it's going to be my function f, which is 2 times the input plus 3. The input to my function is my g function, so 1 minus x squared. So that is my h of x. I can do algebra now and simplify this. Well, really it's just simplification. But we get 2 minus 2x squared plus 3 to end up with a simpler formula for h, which is 2 minus 2x squared plus 3. That's my h. 2 plus 3 is 5. So if I change this to 5 and get rid of the plus 3, that is my composite function. So let's get rid of that, call this h. And as the composite, we can now just work with this formula for it, as opposed to the full putting the g inside of f.